introduction. Miquel Barcelona, and this is a joint work with Alex Aro and Mr. Maria Montelo, my PhD advisor, and where we try to compute heteroclinic connections between these center manifolds using a semi-analytical technique, which is the parameterization method. So in this work, we try to provide a systematic way to study heteroclinic connections by using the parameterization method for computing expansion of invariant manifolds of fixed points of vector fields, which is a technique introduced by Cabré, Fontic, and De la Llave, but our methodology is based on the ideas from the book of Aro, Luque, and so on in 2016. So we provide a method which is general and flexible in the sense that it's independent of the vector field, and we provide also a new style of parameterization to parameterize central and stable manifolds, from which we will try to improve the available accuracy test. So in this work, we present results in particular for the restricted three-body problem for the Earth-Moon mass parameter, but it can be extended. To other vector fields. So in particular, we try to give a family of heteroclinic connections between collinear liberation points in this problem, so that can be used in some sense as a seed to liberation point missions like the Artemis P1 in 2011. So just to be clear, we will set the small mass primary at the left side of the big one. So just to recall the parameterization method, we will start by recalling the parameterization method to introduce our new extra style. And so our goal is to compute a manifold tangent to some eigendirections of a fixed point that we call P, associated to a vector field X. So in order to do that, we diagonalize it by using this linear change of variables, and where we take P as the matrix of the eigendirections that we want our manifold to be tangent to. So our work turns out to be to find a t-dimensional manifold tangent to the first t directions. So we need to find W, which is our parameterization of the manifold, and F, the reduced vector field, which has the system of differential equations associated on the manifold. So our invariance equation that we want to solve is this one, which is the infinitesimal version of the the original one. So in order to solve it, we expand W and F in power series like this, where each one of the components of this sum is a homogeneous vector of order k in S. So we solve this invariance equation order by order. So the first two orders are satisfied by our initial conditions in order to contain the fixed point and to be tangent to the first the eigendirections that we want our manifold to be tangent. So the rest of orders can be solved by solving the cohomological equations, which are these ones, which the first one is the tangent part, and the second one is the normal one. So the normal one has only one solution, which can be solved only when there are no cross resonances. And the first one can be solved using what we call styles of parameterizations. So just to recall that R are all the known computed terms that are terms up to order k-1. So in order to solve the tangent part, we can take A or B depending on what we want to be to simplify, if the F, the vector field in the reduced parameter space, or the parameterization, which would be the chosen B. So at the end, our parameterization style is a rule to choose A or B depending on the indexes I and M, where M denotes the order and I denotes the component. So our new style of parameterization is what we call mixed uncoupling, and is used in order to accomplish two conditions. the first one, let's see an example. For instance, we want that S3 and S4 equal to 0 to be invariant in the reduced space of parameters. So we need to ensure that the third and the fourth component of the vector field is equal to 0 when S3 and S4 is equal to 0. So in order to do that, we choose A if I, the component of the vector field, is in 2 or 3 when M3 and M4 is equal to 0. And the second one, well, just to say that this can be done for several indexes. So we can add more conditions to this constraint. And the second one that we want is to be the first d-1 components of the vector field in the reduced space to be independent of the last component. So they evolve by the reduced vector field independent. The first d-1 components of the vector field evolve independently from what we have at the last component of the initial condition. So in order to do that, we choose the A way of solving the tangent part when we are in one of the d-1 components when the exponent associated to the last component of the initial condition is different to 0. So let's see an example of how can we use this style of parameterization in our vector field, which is the restricted three-body problem. So in our case, we would want to parameterize a five-dimensional manifold, the center stable manifold associated to the L1 division point. So we take as P the matrix of the linear change of variables, which is this matrix over here, where U is the eigenvector associated to the planar eigenvalue of the differential of the vector field, and V are the eigenvector associated to the vertical part, and these W's are the ones associated to the real eigenvalue. So we apply this procedure with n equal to 6 and b equal to 5, using this mixed uncoupling style by setting S5 equal to 0 invariant, S3 equal to S4 equal to 0 invariant, and S1 equal to S2 equal to 0 invariant. This will be also uncoupling the fourth first component of the reduced vector field from the last one. So just a remark, this change of variables introduced by P give us a system of differential equations which is complex. So defining this matrix over here, this matrix C, we can obtain the real manifold by undoing the change of variables that we do by computing this expression over here. So in fact, what we are computing is this W without the overline. So at the end, our real manifold, thanks to these choices of indexes, we'll have that when S1 and S2 and S3, S4, S5 are equal to 0, we'll describe the planarly Lyapunov periodic orbits, and S3, S4 will describe the vertical Lyapunov periodic orbits. Thanks to this order, thanks to this choice of indexes and the order of the matrix P. And then S1, S2, S3, S4, and when S5 is equal to 0, we'll describe the central manifold of L1. And finally, we will have that any point like this with C, with the first component equal to T, will be the fiber of the same point with S5 equal to 0 in the central stable manifold of L1. This is thanks to the choice of these indexes and the coupling of the first four components of the vector field. So once we have completed our parameterization, we would like to obtain a mesh of isoenergetic points, a mesh of isoenergetic slices of the center stable and center unstable manifold, for which we want to see if we can have heteroclinic connections. So at the end, our problem turns into computing the set of points like this, such that satisfy that they are at a fixed level of energy. So in order to do that, we want to find an alternative expression for this formula. So what we have is to consider a matrix like this, like Q, where U sub r, P sub r are the real part of the eigenvectors that we had previously. U sub I and U sub P and B sub I are the imaginary part of these vectors. And with this order, Q can be made symplectic by choosing suitable norms thanks to the J orthogonality of these eigenvectors. So at the end, this change over here, when L sub j is any of the liberation points, takes to a new system y dot, which its linear part is a realignment of its real Jordan form. So the Hamiltonian can check to be this way, this form of the linear part. So since the change is symplectic, we will have that the original Hamiltonian evaluated at this change of variables will be the energy of the Hamiltonian evaluated at y equal to 0 plus the previous Hamiltonian that we have plus higher order terms. So introducing this parameterization into this expression, we have that for any S that is in R4, we have that the Hamiltonian evaluated at the image of a parameterization can be expressed in terms of the S like this. So it's like this plus higher order terms of S3. So this gives us a way to determine whether a point is in this level of energy or not. So by fixing an energy value of H and disregarding higher order terms, we have that S will be in the isoenergetic slice if it satisfies this equation. So at the end, the projection in S1, S4, S2, S4 is an ellipsoid, a solid ellipsoid. So that can be meshed by taking S1, S2 in this interval over here, and S4 in this interval over here, and checking for this equation if it's satisfied for S3. If it's satisfied, then the point is inside this solid ellipsoid. So in order to take into account these higher order terms, we consider the following intervals where we add these epsilon terms. So we make a little bit larger the intervals, and we try to solve numerically this equation over here for S3, where this equation is the original Hamiltonian expression for the original vector field. So at the end, we consider that this equation has no solution if we cannot detect a change of sign for S3 in this interval. So we obtain a way to mesh isoenergetic slices of central stable and central unstable manifolds that can be used later to obtain error estimations over the Poincare sections like this. So we consider the error in the orbit, which is the difference between integrating in the reduced vector field or in the original vector field and using the computed parameterization for any initial condition S sub 0 that we take as the condition over the center manifold and delta changing the fifth component, so we are in the favor of the initial condition and computing the maximum error. So for instance, for a fixed level of energy, we obtain the results of here, computing the maximum error in each S4 for pairs of S1, S2 values. So repeating this process for different values of energy and different orders of expansions, we can obtain the range of validity of our expansion. So until what level of energy we can use this methodology to obtain these isoenergetic slices. So we see that we can arrive more or less between something into these two energies with parameterizations up to order 50. So with this methodology, we can now compute this heteroclinic connection between center manifolds. So as we know, an heteroclinic connection from L2 to L1 is a trajectory that is the intersection between the center stable and center unstable manifold. So what we first do is to compute the parameterization for each one of these manifolds. And and we compute isoenergetic slices for each one of these parameterization, as we said before. And by considering a Poincare section sigma, like can be the position of the small primary, our heteroclinic connections in terms of initial conditions in both the departure and the arrival manifold will satisfy this equation of here, where we borrow notation from Bonnet and Mathemon, where P is the Poincare map associated to sigma, and the sign denotes if the integration is going forward or backward in times, and J and K is the number of cuts with the Poincare section. So instead of solving this equation, which turns into computation of Poincare maps and differentiating Poincare maps, we introduce the times of flight, T super U and T super S, which are the times to arrive to the Poincare section. And we also add, we use multiple shooting strategies, adding points, intermediate points within the stable and unstable branches along these branches. And we solve this system of equations, which this one is the departure condition from this unstable branch. And this condition over here is that both branches matches at the Poincare section. So for this set of unknowns, what we have is a system of equations where we have two more unknowns than equations. So we can use this system to fix some variables in order to look for example, planar heteroclinic connections between planar lapping of orbits or vertical lapping of orbits. So before solving these equations, the system of equations, what we first do is to determine the energy level and the number of cuts with the Poincare section for which we can find heteroclinic connections in center manifolds. So what we do is to compute the planar lapping of orbits and integrate it until the Poincare section, and look if we can have heteroclinic connections between these two periodic orbits, and we try to find these intersections between both images. And if we have, we can compute the isoenergetic slices. And for each point in the isoenergetic slices, what we do is to integrate it again until the Poincare section, and computing its minimum distance at the Poincare section to another corresponding point from the other unstable or stable branch, and well, make these hit gradient maps in order to identify which regions over the Poincare section S4 equal to 0 are more suitable to have heteroclinic connections, and we refine these slices in these regions by, for example, using polynomial interpolation or other techniques in order to obtain better initial conditions to solve our system of equations. So once we solve these systems, just to show some results, these are all the families of heteroclinic connections in terms of the initial conditions in the parameter space for the L1 manifold, the manifold associated to L1 and the manifold associated to L2. And we will have over here the heteroclinic connections between planar lapping of orbits and for different levels of energy. So this would be a description of this family of heteroclinic connections that can be represented integrated by this in terms of X and Y, and also from the view from the Earth, which will be these, where these points over here and these points over here would be the initial conditions on the departure and the arrival manifold. So that's all, just to say that we are trying to extend these results to higher level of energy by means of numerical techniques. And also we are trying to explore this methodology to other systems of interest, like it could be the geostationary belt with the geostationary belt, and also trying to explore properties of these heteroclinic connections between L1 and L2. So that's all. Thank you.